What's up everyone, this is Dariusz Kalbarczyk, co-founder of NG Poland, JS Poland, AI Poland and AngularMaster.dev. Welcome back to the Angular Master podcast. Today, together with Manfred Steyer, who is an excellent speaker, trainer, consultant and author, we will talk about forensic code analysis. Hi Manfred, how are you?
I'm really fine. Holiday is over and now I have to work again. And somehow I'm really looking forward to this because there are a lot of cool projects and conferences and meetups on the horizon.
Okay, let's talk about forensic code analysis.
Yeah, sure. So I think we all know somehow static analysis. It gives us some ideas about the code and the code structure and also the architecture it represents, but it's somehow limited. It's useful, of course. We get out modules and boundaries and if there is a lot of coupling, if everything is intermingled or not. And this gives us an idea where we should look at. However, forensic code analysis goes far beyond this because it does not only look into your source code, into what we have now, it also looks into what happened during the time, how it was produced. And for this, it looks into your source control history. And combining both information give you a way to unveil really nice hidden patterns. An example for this is change coupling. So let's say you have two modules in your application, perhaps two domains or two layers, and you find out that quite often they are changed together. Perhaps there is not an official connection between them because they might depend upon other in an indirect way. But if you change them quite often together, then this is some kind of coupling. Then it's some kind of logical coupling, and this might be an indicator that your architecture needs some improvement here or there, that you should rethink your module boundaries, your domain boundaries, and so on.
So why this topic is important to you and how does it fit with your other discussions on architecture?
Well, the thing is, we evaluate a lot of Angular projects and architectures. Usually people come to us after they have implemented for some person years, and then they tell us, well, we have now this first version of the application and it works. However, we have to make sure it can be maintainable in the long term. Because especially when we talk about business software, enterprise software, it needs to be maintained for a decade or several decades. Just think about banks or insurances or the industry, automotive, things like this. There you have a lot of huge software products that need to be maintained in the long run. And also they need to meet all the other architectural goals they have in the long run. And so they ask us to do an evaluation. And usually we use a mix of reviews. We look into the source code. We went through the source code together with them, and we ask a lot of questions about pain points and other stuff. Stuff like, how do you deal with state management? How do you slice your app into parts, like into domains, layers, modules? How does your team structure align with it? And so on and so forth. And together, looking at the source code and getting answers, we can give some advice and we can help them to make the software more maintainable in the long run. And the idea now is to support this process with some quantitative data. Because so far all of this is more or less qualitative. We are asking questions, we are looking into the source code, we are bringing in our experience. And the idea is to bring in also some quantitative data to support this. And yeah, this is where forensic analysis, that tells us a lot of stuff about the creation of the software by also analyzing the source control history, mainly your Git history, comes quite in handy.
Can you tell us more about Detective?
Yeah, so it's an open source project and it implements some of those ideas from the area of forensic code analysis. Saying this, they are also commercial products and we don't want to compete with them. We just want to have some of those analyses for supporting reviews or for finding out at one glance, well, let's look here in the code base or let's discuss that. We have a dependency graph, which has nothing to do with forensic analysis, but it's more or less the first thing you want to know about your application. How is everything structured and how do the different modules, domains, layers interact with each other? Is there a lot of coupling, for instance, or is there no coupling? And this gives us a first idea of the application. And then we implement several forensic analyses like change coupling or other analysis we will hopefully talk here in this interview about a bit later. And the best thing about Detective is you just go into the root of your application and start it with npx. npx and the name of the project, then it starts up and gives you an idea of the healthiness of your application by analyzing the code structure together with the Git history.
You mentioned change coupling. Can you explain what it is and why it's significant?
It's about finding out which files are changed often together. Let's say we have two different modules, but we find out in 90% of the cases, those modules change together. Then perhaps our modularization needs to be questioned. And this is one of those ideas we can get from change coupling. You can do this on a per file level. You can say, well, those two files are really coupled. They are changed together quite often, but we are aggregating this on a module level, like on a domain level, a layer level, or some other kind of module to find out if we need to improve our domain boundaries, module boundaries, and so on.
How can we determine which file have been changed together?
There is an easy way and there are some further better ways. The easy way we are currently implementing, and I think it's good enough for a lot of projects, is we just look into the Git commits and we look into which files are in there. And if we find files of several modules in one commit, then we have some change coupling. Then at least internally, we can increase our counter for the change coupling of those modules. And if we find such a situation again in the next commit message or in some other commit message, we are further increasing its counter. And then we can visualize all of this with some nice graph that shows us thick connections between modules that are changed often together and no connections or very thin connections between modules that are not changed that often together. I think this is something that works quite nicely in a lot of projects, but in some situations we need to do better. There is some room for improvement. Commercial tools implement those better strategies. Perhaps if I find some time, I will also implement them. One idea is to look if your commits come from the same feature branch. If they come from the same feature branch, then this is also an indicator that perhaps they are coupled together. Because that means for implementing one feature, first of all, I needed to update this module, and then I needed to update that module. And then we could also look into our commit messages. A lot of teams place a ticket ID in the commit message. And if we find out, well, we have 5 different commits with the same commit message, then we can join them together and group them to a logical commit. And then we can also try to find out if several different modules have been modified when implementing this or that ticket. So there are several ways, but it's all about looking somehow into your Git history.
Let's say we find out that we have a high change coupling in some areas of our software. What should we do with this information?
This is a sign that we need to question our module boundaries. And the thing is, coming up with good module boundaries is really, really difficult. There is no methodology that really helps you there. And that's why I like domain-driven design, especially the strategic part of it, strategic design, because it at least gives you some heuristics and some ideas that guide you. But it's not bulletproof. There are no silver bullets here. But let's say you have domain-driven design, especially strategic design. You have defined your domain boundaries. You have implemented some of the patterns there for decoupling domain boundaries. Even though you have done all of this, you might find out, well, it does not work that nicely. You might find out we have to change a lot for this or that use case. And of course, your guts give you that feeling. That's why we really like to interview developers when we do an architectural review. They really have a good feeling for what works and what does not work and what works under which circumstances. But also change coupling gives you an indicator that points into this direction so that you can come up with better questions. And if you ask me, this is one of the most important things an architect and consultant can do, asking good questions. And then perhaps we find out, well, even though we have used all those patterns, we need to improve our domain boundaries somehow. We need to refactor it. Meanwhile, we are lucky because most people have accepted the fact that from time to time, we need to refactor our application. We are constantly learning when we implement a piece of software. And that means after implementing stuff for a year, we hopefully know more than we have known before. And somehow we need to respect this. And now those learnings can be respected to question those boundaries. Perhaps we need to move some features around to have less coupling between our modules. Perhaps we also find out that we need to split one of our modules. Perhaps there are no clear responsibilities or too many responsibilities in there. So if you have a module that cooks your coffee and that writes your invoices and that manages all the atomic power plants, the nuclear power plants in your neighborhood, perhaps it has too many responsibilities, and that means you need to split it up. And this is where it becomes a bit more difficult. I always say satisfying a linter is kind of easy, but questioning those responsibilities, those boundaries is difficult because it demands that we really wrap our brain around this piece of software and that we come up with a better modularization. So it really involves more brain capacity than just changing this line of code in a way the linter is satisfied. But at the end of the day, this really pays off because it gives us modules that can be more or less changed independently. I can change something here with less fear that I break something over there.
You are now listening to the Angular Master Podcast by AG Poland. Listen, code, repeat all you need to know to become a super Angular developer. Make sure to hit the subscribe button and drop us a cool comment. And don't miss out our second show, the JavaScript Master Podcast, where you find tons of fantastic JavaScript topics. Another key concept in forensic code analysis is hotspots. Yet exactly is a hotspot?
Yeah, this is also an idea that comes from forensic code analysis. Perhaps it's even the main idea. It's about identifying parts of your software that are very likely problematic, that will very likely cause a lot of pain in terms of course, bugs and reoccurring bugs and so on. And for this forensic code analysis is using a metric where meanwhile we have some evidence that this metric really tells us this might be problematic. I really say this might be problematic because we are just talking about indicators. Let's see it as an invitation to a good discussion, an invitation to look into the source code a bit closer. And this metric is code churn. The thing is, we have found out, and there are several studies around this, that if the same file has been changed time and again in a very short time period, then it might be problematic. Then perhaps you don't really understand the requirements, or perhaps it has too many responsibilities, and so perhaps we need to split it or refactor it. When we talk about all of this on an architectural level, we don't just look at code churn at a file level, but we aggregate it to the module domain layer level to have an idea about which domains layers are more problematic than others. However, just having a high code churn is perhaps an indicator that this file might be problematic, but what to do if we have a high code churn in thousands of files? Then somehow you need to have a prioritization. Then you need to somehow weight this code churn with another metric. And this metric is code complexity. That means we also analyze the code for its complexity, and then we try to find out which are the files with a high code churn that have been changed quite often and that are also very, very complex. And those are the files we should look at first. So this gives us some kind of prioritization, because honestly, not each and every file in a huge enterprise application will be perfect. And so we need to find a way to focus on stuff we really should look at, we really should question. And so, yeah, we weight the code churn with complexity.
How do we evaluate the complexity of a code file? Are existing metrics effective?
Yes and no. There are a lot of metrics out there. I think we have these metrics for decades. Perhaps they are even as old as computer programming. And finally, we have meanwhile some evidence that those complexity metrics are really bad at one thing, namely at forecasting complexity. So there is some evidence, there are some studies where people have been shown different code files, and then they got some questions about those code files. And then the scientists looked at the code file if the questions have been answered correctly. And they also measured the brain activity of those people. And when doing this, the findings were, well, there is some correlation between those metrics and the perceived complexity, or let's call it the cognitive load of people that needs to understand this piece of software code. But this correlation is not really high. It's low to medium. And yeah, that's why they are never, ever perfect. But nevertheless, we need some way to measure the complexity. And I think the classical way of measuring the complexity is the so-called cyclomatic complexity, the so-called McCabe number or the McCabe metric. And basically, I think it can be understood quite intuitive. It's about finding how many paths go through your software or through this piece of software, through this file, through this function, through this method. And so, simply speaking, it is counting all the ifs and the switch cases and the loops and the catch blocks and so on, all the different paths that go through it. Because the idea here is the more paths go through a software or a piece of software, the more complex it is. Which might be true in several cases, but not in all of the cases. It really also depends upon how the software is written. But it's a simple metric and it's a widely known metric. Most of the tools out there that try to evaluate your complexity implement this cyclomatic complexity. There is another metric that is almost as good as cyclomatic complexity, but it's really drop-dead simple. The idea is quite young, and we have evidence that shows it's really as good as the more complex cyclomatic complexity. And it's really funny. It's just about counting intentions, because every time we do an intention, we add some complexity to the code. We have an if, we have to consider when reasoning about the code, we have a loop and something like this. Of course, no one forces you to intend your code, but if you don't intend your code when you have an if or a while or something like this, you have a different problem. Can someone should hit your fingers, then you should not survive the next code review, then your pull request should not land. And in times like this, very often we have something like Britia that does it for us. So this is also a way to measure how complex your software is. The more intentions we have, the more different paths we have to respect. This also correlates with nesting levels. However, if you just measure the intentions at the beginning of your line, you can implement this once and it will work with a lot of programming languages out there. Everything beyond assembler code, I guess, will work. It will even work with HTML somehow. Of course, you cannot compare the complexity you measure that way of HTML with the complexity of a TypeScript file, but it gives you some way to say, well, this HTML file is for sure more complex to reason about than that HTML file. And this is really funny because it shows that simplicity quite often wins. There is another very simple metric that has proven to be effective, also in the study I mentioned before, namely code length. Because at the end of the day, it's all about cognitive load. Does it fit our brain? Can we look at it after 6 months and find out without debugging it for 2 days what this piece of software is about? So it's all about cognitive load. And we have a lot of evidence that the size of the code really matters when it comes to cognitive load. And yeah, this one more time shows us that short methods, and I think this is also a best practice when it comes to clean code and other disciplines, and short files really helps. And honestly, I really like it because it's really more focusing on the human side of software development. It's not focusing that much on the syntax. It's focusing on our brain capacity, on how our brain works when we try to find out what's this function is about.
You mentioned there is no strong correlation between complexity metrics and how developers pursue complexity. Why are those metrics still used?
You're right, there is no strong correlation. But in our case, in the case of forensic analysis, we are lucky because we have code churn and we just need to prioritize code churn. Let's say we have found out that all those files there have a high code churn, and perhaps we have some files there with a low complexity, perhaps a file that is just informing us about all the features in the software. It might be the basis for our menu items. There is less complexity in there, but it needs to be changed every time we add a new feature, obviously. So this prioritization tells us that we will rather not, first of all, look into this file, but perhaps in another file that has a really difficult algorithm, a compiler or something else with both a high complexity and a high code churn. So it's all about getting priorities because we cannot analyze everything at once. And it's just a pointer to something you perhaps should look at and you should at least discuss.
Once we identify some hotspots, what steps should we take next?
So also a hotspot can be a sign of an issue with your architecture. Perhaps you don't have good module boundaries. Perhaps you have something some people call a God class, a class that has too many responsibilities, or a class that somehow bleeds in the responsibilities of a lot of areas. And in this case, somehow you need to split it up into several responsibilities, or perhaps into several domains, or into several modules. But there is one thing that is even worse than a huge hotspot. It's a huge hotspot with a lot of coupling. So in this case, we already have two indicators. And I really like this because honestly, there is no silver bullet. We just have weak indicators. Of course, there is some scientific background there that bakes our analysis, but after all, we have weak indicators. But if we have several weak indicators pointing into the same direction, and if this fits to your gut feeling and to what your developers tell you, and to all the issues you have on a regular basis when you want to ship a new version, then you really should look into it. So it's about combining weak indicators.
You also write about and implement team code alignment in Detective. Can you explain what this analysis involves?
So at first glance, this might sound funny because now the architecture guy is looking into your team structure. But also there, meanwhile, we know that since several decades that your code structure always mirrors your team structure. This is known as Conway's law, and Conway defined this law in the 1960s, in the late 1960s. And it's not a law, it's more of an observation that your application structure, your architecture mirrors your team structure. And there is a very simple way to explain it. If I want to explain it in very simple terms, I would say if you have 3 teams implementing a compiler, you get a compiler that consists of 3 phases. If you have 3 teams and if they work on a very difficult analysis, then also very likely this analysis consists of 3 phases. Because somehow the team structure is mirrored there. Somehow we need to decrease complexity. We also need to focus on one aspect, and we need to decrease the amount of communication between teams. I don't want to stand up for every line of code I have to write, go over to the next team and discuss my line of code with all of them. This would really slow us down. That's why this observation might be right. And yeah, that's why we are also looking into team code alignment, which basically tells us if our modules are mainly updated by one team. For this, one more time, we can look into the Git history. There we have the usernames and their email addresses, which are kind of unique. Then we can map those usernames, email addresses to teams, and then we see if there are clear boundaries between teams, or if one team has to change code of another team quite often and vice versa, which gives us all those negative effects of slowing everything down and having more complexity, because we not just only need to have our work in mind, but also the work of several other teams.
What should we do if we find weak team code alignment?
Yeah, so if we find out that the code team alignment is really weak or not existing, then we should think about aligning the team structure with the code structure a bit more. This is sometimes called the inverse Conway's maneuver. Conway's law tells us that the code structure follows the team structure. And the inverse Conway's maneuver tells us, well, if we know this, then let's define the teams in the same way we want the architecture look like. And then we use this effect to get the architecture we want to have. That means we don't want to fight Conway's law. We use it so that we have a team structure that represents our code structure we want to have. And this is done quite often. The whole micro front end and microservice community is about this. It's about having several parts of software that can be managed by autonomous teams, by teams that don't need to coordinate that much with with each other. But we also have this in monolithic applications, because also monolithic applications are sliced into modules, layers, domains, stuff like this. And somehow we also want to have those effects there, those effects of autonomous teams. In this area, I quite often speak about modular monoliths or moduliths, which is a modular application that is also monolithic, but internally it's sliced into pieces that can be managed by autonomous teams. However, such a diverging team structure, if the team structure is diverging from the code structure, this might also be a sign that people officially are grouped according to domains, but perhaps de facto they are working in their old style. On the paper, we have grouped them nicely, but in real world, they are just touching everything. They are working like before. Or perhaps even worse, perhaps they are aligned with technical aspects. Perhaps we have one team that takes care of data access, and another team that takes care of the backend services, and another team that takes care of the front end. And I think meanwhile, the common knowledge is that we really want to avoid such layered teams, because there we don't have any end-to-end responsibility. And every time something does not work, the team is saying, well, I'm not responsible for this. It's the fault of the front-end team, or it's the fault of the database team. And that's why for years, perhaps even for several decades, we really try to have end-to-end responsibility, to have vertical architectures where one team takes care of end-to-end business functionality. Or to put it in other words, it takes care of producing business value. This does not mean that everyone in the team needs to be a full-stack developer, but the team as one unit has this responsibility for implementing this, let's call it domain, invoicing, or the shop, or perhaps something like, I don't know, sending out a reminder for an event, or sending out tickets for an event. End-to-end responsibility for just one part for one domain of the application. So before I told you, it's important to align the team structure with the code structure. This is not fully possible anymore. In practice, it's a bit of both, aligning the one to the other and the other to the one. And so also we get at least more of this alignment that correlates with Conway's law. And the result of this is really beautiful because one more time we are reducing cognitive load. We can concentrate as a team on one aspect. We have clear responsibilities and less complexity because we don't need to think that much about the stuff that happens in other teams. Saying this, there are no silver bullets, but yeah, improving this towards this direction is for sure important and, as mentioned, done by a lot of communities nowadays.
Detectives allow you to break down team code alignment to the developer level. How does this help?
First and foremost, Detective tries to stay on the architectural level. That's why the first diagrams we see in there and the first reports we see in there are always aggregated to the modules. But of course, if you find something that looks not right in there, your first intention is to drill down to the code level or to drill down in the case of the team code alignment to the level of the commits of individual persons. And yeah, that's why we allow this drill down. And it's also interesting to see who changed what, not because we want to blame people or because we want to say, well, you are lazy. I hope meanwhile we learned that this is not a good measurement, that someone who writes more lines of code is less lazy than someone else. This is more about finding out other nice patterns, like what happens if those 3 team members are leaving the team. Do we lose a lot of knowledge about the software? Do we need to split our team members a bit better so that more people within the team know about those complicated code files? What's our drug factor? Or did we already lose knowledge? It would be interesting to map some people to an artificial team called former team members to find out if we already lost a lot of knowledge about critical parts of our application.
That all sounds promising, but I'm curious, what are the limitations of forensic analysis?
Yeah, so I think this question is really important because I already mentioned several times this is not a silver bullet. For me, it's a way to support us, to support architects, to support technical decision makers, to support consultants, to ask better questions. It's really as simple as that. It's about asking better questions by unveiling some patterns that are not obvious. And perhaps people say, well, that's fine. Let's go over to the next question. And perhaps they say, well, that's a good idea. So let's investigate this. Let's discuss this. Perhaps we can improve it. However, it's just a pointer for asking questions. It's not a replacement for qualitative analysis. And I think first and foremost, code analysis, architectural analysis is a qualitative issue. It's about reviewing the code. It's about looking at your goals. It's about talking to people. And I found out that talking to people is the most important aspect there, because developers really have a good gut feeling about all the pain points, because they see the pain points and they feel them on a daily basis. So if you don't do a review against them, but with them, for them, normally they are quite supportive and give you hints like, well, let's start with this portion of the software. It gives us a lot of pain because, of course, as a consultant, you cannot read all the lines in this huge application. So, you need to ask them questions, and then you, of course, bring in your experience to look at this or that, and you bring in typical topics like, let's talk about state management. How does it work here? Do we find better ways for doing it? Let's talk about modularization. Let's talk about how you use signals and effects to come up with a quite recent topic, because it's quite a new topic in the Angular space. So it's not a replacement for all of this. It's also not a replacement for thinking about what are your goals and what are our trade-offs regarding achieving those goals, and are there better architectures? Can we fine-tune our architecture to have less trade-offs, or to have less trade-offs of this kind and more trade-off of that kind that is not that painful for us? And so, at the end of the day, even though forensic analysis is amazing and gives us quantitative measures and give us nice pointers, at the end of the day, it's qualitative. And so forensic analysis can just support this kind of things, but not replace them.
If a team wants to improve its architecture, what steps would you recommend?
First of all, we need to know about your architectural goals, and we really need to bring them in an order, because otherwise you will achieve none of them if you don't prioritize them. Just to give you an example, of course, something like usability is super, super important. But I have seen some projects where the ability to change the code easily was more important. Think about accounting. There are a lot of laws, and we need to align with those laws. And the laws are changing. And even though they are changing, we need to implement a new law. But for the data of the last year, we still need to apply the old law. And that's why those people said, UI is important. But more important is we need to be able to change it. Just an example you would not think about, especially not as a front-end developer. But you need to bring your goals in some kind of order. Perhaps you say autonomous teams is not a goal for us, or you say it's super, super important because we need to outsource this and that part of the application to other developers, and that's why they need to implement it in an autonomous way. Or you say, well, we are really nice people, we sit together, perhaps there are even 20 people, but even though they don't need to go with strict boundaries so that they have autonomous subteams. So it really depends on the goals. This is the first thing we need to investigate. The second thing is to investigate pain points. That's why I like to go with interviews. Then you look into your code. You find out if you can lower the pain points somehow. And you find out if there are better ways to meet your goals, because you have always some trade-offs, but perhaps you find some alternatives with better trade-offs. So it's all about this, knowing your goals, knowing the current situation, the pain points, and discussing candidates, architectural candidates for improvement. And as mentioned before, this sounds quite easy and it sounds like just a process. And the process is important, but it's also important to have people in the team that are not blind. If you work with the code bases on a daily basis, then you might become blind. In German, we say, you see a lot of trees, but you don't see the whole forest anymore. And this might happen if you are too deep into your code base. And you need a lot of experience with architecture in general, but also patterns that are usual in the Angular community. And that's why a lot of companies ask us to help them with such an evaluation. And usually it takes some days. And then we have a lot of tasks. We can prioritize them. And if you implement those tasks, they help you to make your code better in terms of maintainability, but also in terms of reaching your goals, your architectural goals.
Could you tell me what you prepared in the new version of the video course?
Yeah, so what we did is I call it DNA is still the same. The DNA of our workshop is domain thinking, slicing the application into parts that don't need to know much about each other, implementing those slices with micro front ends or with a modulet, with some layers, with modules, and all of this without Angular modules because we want to go with modern Angular. And it's all about data flow in there, in the sense of our XJS and signals. So this is the DNA of this, and this is not changing. But two things are added. One thing is we are talking, obviously, more about signals, because this is the new cool topic everyone is interested into. And also because it's really influencing how our architecture is implemented, because it's influencing the data flow in there. And there are several misconceptions and there is a lot of confusion because signals are not intended for everything. That's why we still mix and match it with our XJS. This is one aspect that's brand new. And I will also tell you how to use them in a safe way, so that you don't run into pitfalls. And another aspect is we look into state management with the brand new NGRX signal store, which is fully signal-based. It's lightweight. It's not Redux-based. Saying this, we also discuss when Redux makes sense and when you should think about something that's more lightweight. And we also show you how you can update or enhance, modify your signal store with custom features so that you just need one line of code for repeating use cases. And when doing this, you can also re-implement Redux on top of this very, very lightweight signal-based store. Yeah, those are the big new chapters in there, and they are really cool. And they really fit well to our architecture and also to our general architectural, let's call it DNA.
Manfred, it was amazing as always to have you here. Thank you. Thank you so much for your time, for your knowledge. And it is a pleasure for me to talk to you. And I am looking forward to see you on NG Poland.
Yeah, same wise. I'm also looking forward to NG Poland. It's one of the best events of the year, and everyone should be there, by the way. And yeah, I'm also looking forward to all the other stuff we are planning to do together.
Thank you,
See you
sir.
around. Thank you.
Thank you. Bye-bye.